Welcome to a video in Chemistry Topic 1. This video will focus on the groups of the periodic table. In this video we will look at the alkali metals, they are the group 1 elements. Then we will look at the halogens, the group 7 elements, and then finally we will look at the noble gases. They are the group 0 or group 8 elements. In the next video we will look at the transition metals, as this is a triple only topic. In this first part of the video, we will look at the group 1 alkali metals. We will look at their properties, we will look at their reaction in water, and we'll have a look at why the reactivity increases down the group. Our big question for this first part is explaining why the alkali metals become more reactive as we travel down the group. So, what are the alkali metals? The alkali metals are the group 1 metals. These are the metals on the far left-hand side of the periodic table. The group 1 metals are all highly reactive. They are also very soft and have low densities. The three that you need to know are lithium, sodium and potassium. Lithium has the symbol Li and is the smallest of the alkali metals. It's very much the little brother of the family. Our next alkali metal is sodium with the symbol Na. Sodium is more reactive than lithium, which we will look at on the next slide. Finally, we have potassium, which has the symbol K. It is the most reactive alkali metal that you need to know about. All of the alkali metals have one electron in their outer shell. It's what makes them group 1. If you're unsure about electron structure, please watch the previous video. As we go down the group, this outermost electron gets further away from the nucleus because there are now more shells. Because this electron is further away from the nucleus, it is more easily lost to a non-metal in an ionic bond. This means that as we go down the group, the metals get more and more reactive, with lithium being the least reactive and potassium being the most reactive of these initial three. This means that as we go down the group, the reactivity increases. As we go down the group, the melting and boiling points also decrease and the atomic mass increases. As previously mentioned, as we go down the group, the melting point decreases. The alkali metals also become softer as we go down the group. You also need to know how they will react with water. All of the alkali metals react with water to form a hydroxide and hydrogen gas. Lithium will produce lithium hydroxide, sodium will produce sodium hydroxide, and so on. As we go down the group, this reaction also becomes increasingly violent and vigorous. Lithium will fizz on the surface. Sodium will fizz more, can catch fire, and will skate around on the surface. Potassium will burn with its trademark lilac flame. Rubidium will undergo a fast explosion, and then finally cesium will undergo a very fast and very large explosion. The alkali metals also have various uses. Lithium is used in batteries, for example in mobile phones. Anything which has a lithium CAD battery uses lithium. It can also be used to treat depression. Sodium, interestingly, is used in street lights to produce the trademark yellow glow. It's also found in common table salt. Potassium, as you will look at in NPK fertilizers in the triple chemistry unit, is used in fertilizers, soaps and detergents. It's also found in bananas. Finally, we have some uses for rubidium, cesium and francium, although for GCSE we do not look at these metals. The second part of this video will focus on the halogens, which are group 7. We will look at describing and predicting the properties of the halogens. We will have a look at how they react with the alkali metals that we looked at in the previous section to form metal halides and as well as looking at the reaction with hydrogen to produce hydrogen halides, and we'll have a look at why the reactivity of the halogens increases as we go up the group. Our big question: when chlorine is added to a solution of potassium bromide, a colour change is seen. When chlorine is added to a solution of potassium fluoride, no colour change is seen. Explain how these observations provide evidence for the order of reactivity of bromine, chlorine and fluorine. At GCSE, we focus on 3 major group 7 elements. These are chlorine, bromine and iodine. Chlorine is the second lightest of the halogens. It is a dangerous and toxic yellow-green coloured gas that, I'm sure you're aware, is used in swimming pools. It can also be used as a chemical weapon. It's very reactive, but less reactive than fluorine, which sits at the top of group 7. It can be formed by the electrolysis of brine, which we will look at in electrolysis. Importantly, it is a gas at room temperature. It has a very low melting and boiling point. The second member of the family that we look at is bromine. It is the third lightest halogen and sits just below chlorine in the group. It's still quite reactive, but a lot less reactive than chlorine. It can, however, be produced in very high quantities and is used to produce flame retardant objects as well as used in water purification. It is a liquid at room temperature, so it has a low melting point and quite a low boiling point. However, it is a higher melting and boiling point than chlorine. Finally, we have iodine. Iodine is a dark purple coloured solid and is the second heaviest halogen, sitting just above astatine and below bromine. It's still fairly reactive, but it's a lot less reactive than bromine. It melts at 113.7 degrees and so is a solid at room temperature, meaning that it has a much higher melting and boiling point than bromine does. So what are the trends of group 7? I want you to pause the video now and I want you to write down the trends that you can think of based on the information we have just talked through. So, the trends of group 7. First of all, they become much less reactive as we go down the group. This is because the outer shell is further from the nucleus, so it's harder to gain an extra electron because of the lowered attraction between the outer shell electrons and the nucleus. As we go down the group, they also have much higher melting and boiling points, going from gases to liquids to solids, and they have much higher relative atomic masses. However, similar to the group 1 metals, they also have things in common. For example, they are all non-metals, and they all have 7 electrons in their outer shell. Due to having 7 electrons in their outer shell, all of the halogens form 1- ions called halides. These are fluoride, chloride, bromide and iodide. All of the halides will react with the group 1 metals to form metal halides. The group 1 metals are particularly useful with this, as both group 1 and group 7 are highly reactive. Group 1 forming a 1+ ion and group 7 forming a 1- ion. In order to form sodium chloride, we can react sodium metal with chlorine gas. This forms sodium chloride, better known as common table salt. The halogens can also react with hydrogen in the same way to produce the hydrogen halides. For example, we have chlorine and hydrogen making hydrogen chloride. All the hydrogen halides are water soluble and produce acids when they react with water. Hydrogen chloride dissolved in water is known as hydrochloric acid. The halogens are often represented by an X. This means that it could be any halide. They will also react with aluminium to form the aluminium halides, AlX3. We can test for the halides using indicator paper, which will show them to be acidic, as well as using silver nitrate solution. This test for halides using silver nitrate solution is only examined in triple science. We will look at it in more detail in the testing for ions video. A popular examination question looks at the displacement reactions. This is when a more powerful halogen is added to a salt that contains a less reactive halide. This means that the more powerful halogen steals the partner of the less powerful halogen. For example, if we add chlorine gas to a solution of potassium bromide. Chlorine is more powerful, more reactive than bromine, therefore it is able to steal the potassium, forming potassium chloride and bromine. However, if we were to add iodine to a solution of potassium bromide, then iodine is not powerful enough to steal the potassium, so there would be no reaction. Our final topic in this tutorial video is Group 0, sometimes known as Group 8. These are the noble gases. We will have a look at the noble gases and their chemical symbols. We will have a look at the properties of the noble gases and their uses, and we'll have a look at the physical properties of the noble gases. We will also look at our big question, which is how do the properties of argon and helium determine their uses. 5 of the noble gases are on the screen at the moment. The last one is radon. Radon is highly radioactive, so we do not look at it at GCSE. The ones you need to know are helium, neon, and argon. Further down the group we have krypton and xenon. So what are the noble gases like? Well, first of all, they are all highly unreactive. This is because they already have a full outer shell. Because of their full outer shell, they all exist as monatomic gases. This means that they are single atoms and are not bonded to each other. All elements in group 0 are colourless gases at room temperature. They are also non-flammable. This means that they will not set alight. However, as we go down the group, we do get a change in some of their properties. The major one being their boiling point and melting point. As you go down the group, the boiling point and melting points increase. This is because of the increasing number of electrons, meaning there are greater intermolecular forces that need to be overcome in order for the substance to boil. We look at intermolecular forces in more detail in the bonding tutorial. Using this knowledge that the boiling points increase as we go down the group means that we can predict the boiling point of each noble gas. For example, if radon and krypton have boiling points of -62 and -53, what would be the boiling point of xenon? By working out the midpoint, this gives us a boiling point estimate for xenon of -108 degrees Celsius, which is pretty much exactly the correct value. You also need to know some uses of the noble gases. Helium is used in balloons, neon in signs, argon inside halogen light bulbs in order to ensure there is no oxygen so combustion cannot occur, and krypton is used in laser eye surgery. So how were the noble gases discovered? When Mendeleev was originally putting together the periodic table, he knew nothing of the noble gases because they're incredibly hard to discover. Why do you think that they were hard to discover? The reason they were hard to discover is that they don't react with anything. As such, they were actually discovered by accident. Chemists who were looking at nitrogen found that the density of nitrogen made in the lab was different to that they got from the air. This made them think that there must be something else in the air. This something else was the noble gases. So, how did this work? In the lab, pure nitrogen was made, which was found to be less dense. The nitrogen we got from the air was much more dense. By using fractional distillation and cooling down the air, they were able to fractionally distill off the various layers of air as the gases became liquids. As they went down, they found xenon, krypton, argon, neon, and then finally helium. Importantly, for the evolution of our atmosphere, they found argon. As a conclusion to this tutorial video, we have the three big questions. We have looked at why alkali metals become more reactive as we travel down the group. We've had a look at the idea of displacement reactions, and we've had a look at argon and helium, looking at their properties and starting to examine their uses. Helium, for example, can be used for balloons as it is less dense than air. Argon can be used for light bulbs because it is non-flammable and inert. The next video in this series will focus on the transition metals, which is a triple chemistry only topic.